Hey everyone, welcome to Engineering with Mahadev. So this is a session on simple key value database. This is a persistent database where it's not an in-memory database where we will try to store the keys and values directly into file system and retrieve it, properly, even after shutting down the server. So it's not a volatile database. So it's a non-volatile database, right? It's something that I was thinking to build for a while. I know that there are rocks, DB, and all those things which are capable of writing into file systems and all those things. They maintain the SST tables, name tables, Bloom filters, right? So many so many keywords that are there, but we don't really get to use any of those, right? Those are already built, done, and dusted, something like that, because they maintain those internally, and we don't really touch those things. We barely take the wrapper of RocksDB and maybe build on top of that, which is quite good as well. I mean, because once it is built, why do we need to touch those again? So, what if we try to build something, right? Especially, I'm not trying to compete with RocksDB or something like that, which is written in C++, and it is a very good database, right? This is just an attempt to how we can possibly do it, and what are few strategies that we can take, right? Something that I took is what I'm trying to explain over here. So Gostore is a simple database, right? It's not an in-memory database, it's a persistent database. Um, as the diagram shows, so we have multiple databases, we have multiple tables, we have multiple files, right? So here database, we can consider those as folders, right? We can have multiple folders, and each database carries some sort of metadata, right? Who created this, at what time it created, who's the owner of this database, and all those stuff. Those can be saved into that, and when it comes to tables, the same sort of procedure where you have a definition of the table can be stored as table metadata, and tables itself is a folder. Inside the folder, we can keep the metadata file, and you can use that. And there is for tables, right? Finally, the data needs to be persisted down somewhere. So which comes to files, we can say table 1, table 2, table 3, table 4. All these are files where the actual key values are persisted or written. So file needs to get opened, and file needs to get closed, and before closing it, we have to read and write into these files. Those are few aspects of these this sort of database, essentially. So that's the approach that we want to take for building something like this, right? And on top of this, we need to have a TCP server, right? We have to write a TCP server so that clients can connect to it and write and read all this data from the file system. And we will also have to maintain a cache so that we don't end up calling every time. So syscalls and OS calls are, pretty nice out front, but it is not nice because it comes with a cost, actually, right? If let's move into the code. I have written few things. There are DB manager, table manager, file manager. These are few things that I have mentioned right now itself. When we go into the code, you can see a simple data test DB test table. करके. Then we have a test table 0. So this is something that was written and it is there. So we can retrieve it if we start our server and our client, so that if the client gets accepted to the connection, so then we can retrieve this value. And there is metadata, right? So this is test tables metadata. So these are few things that is maintained for there are blocks. So we store with blocks. Test one table can have, let's say, 1024 blocks, and each blocks will have a 4096 bytes of size, which means that 4 KB size per block. There can be 1, 2, 3, and up to 1024 blocks, right? So, um, 4 KB into 1K, so which means that 4 MB is the maximum file size that we can get. So after this, we'll create one more file. And if all the blocks are done and dusted, we have to create table. So this is table 0. There will be table test table 1, test table 2. So those are internally managed. So whenever we have to search, we have to go through all these files. So we will go from the backwards, right? So if there is test table 50, we'll search on the test table 50, and if it is there in the test table 50, then we will return it. If it is not there, then we'll have to search on the rest of the tables. So there is, two attributes called min key, max key. These are to check whether that key is itself is present in the table metadata. So this is for test table 0. So if the test table 0 has that key or not is basically one small check that we can do. So here comes the concept of Bloom filters, right? This is not a fairly good way of checking it. Uh, we can check it, and we have a block level check as well. So block level, we can check whether a key is present or not, I guess, right? Um, so the idea of Bloom filter comes in then, when we can say that we can encode that Bloom filter into this whole file as well. That with a probabilistic approach, we can determine whether that key is present or not. Then we will load the data. Right. That is far better approach, which is not implemented, and because I haven't implemented it, but it's the right way to do it. You know, and this is something I have shown before. And there is this test table metadata. This is just basically the metadata of all these things. How many all the files are will be shown here as well, right? We'll quickly start the server and see how it works. Maybe, right? We are starting the server at 8080. Then once we have started the server, we will connect to the server with this client that we have created. Now here we can get the key value that is already stored, right? Here. Um, yes. So we get value 1, so which is what I have shown before, right? Now put this D. Now it says we have already put the value of kn value into the database. Now, suppose if I try to get it back, we get value. So if I go and check this, and we'll see whether it is written or not. I think it hasn't written. So there should be a periodic flush, which is not there. So if the server stops, it flushes into the file system. Now we can stop the server in multiple ways. We can put Control C and stop it, and we can also kill the process. So if anything happens, there should be a differ function which should write this into the file system. That is the cool part, right? I mean, right now I am doing Control C, and I'll start the server again. See, there is modification on all these things, right? We got the value. So, that's how it works. So I think it's stored in the second block. That is one more thing actually. If the block that is already there, it is not completely filled, we can reuse that block. So probably whenever we start, it should not, check what was the last block that we wrote, and increment and persist in the next block. Instead of that, if we can load entire whenever we are going to flush, if that block is not empty, and calculating the sizes and all those things, and writing to that same block, that can save memory. So which is not there, but still it's a persistent database, right? So anyway, we'll go into the implementation part, right? So we have a controller, which is, and we have a server that takes in the controller, and dependency. And these are few parsers, that we need to use to, create this database, create this table, and all those things. And we have so from once it is accepting the connection, it will call the go routine to call this. I mean, handle the connection, right? So these are few commands that are written over here, which is also there in the README as well. We can also show you a few other things. Maybe create db test db1, and create a test db1. So here there's modification. So here you have a test db1 as well. Now create the table test. So it created the test DB on table one as well. So this is how it works. Basically how you create these things, right? And finally, when you handle the connection, so it has to execute the command actually. So there are parsers and all those things, which does the passing for all these inputs that we are providing as via TCP connection, right? Raw string, so you have to do the parsing and lexing and all those stuff. Thanks to ChatGPT and Cursor, it wrote a couple of these things, right? And when we have an execute command, db table, these are few simple commands, right? You have to create a directory, create a table, um, and all those things, right? So you have few checks whether that is existing or not. If it is existing, you have to throw an error. So if I try to create again, I get an error that it already exists. So these things you need to cover. Other than that, we have execute get. So whenever we will write direct to the get actually. So there are, so here it will call the table manager. So here table manager has, so the metadata that I have been speaking before. So there are caches for metadata. This is the create table function where it tries to create a table where this is a when you want to get something out of the table. So this is something that we do, and this is the files -1. So you search over the files to get something, and here when you go inside this get, right, so first it will check whether the current buffer map has the value or not. If it is there, then we can return it, right? This is for deleted entries, right? We have to check. So whenever we store a value, uh, it's a ledger. We basically track everything, right? Until the compaction happens. So once we store all these things, these deleted entries will also, these will be tombstones. Only the compaction can remove these exactly from these files, and create a new file out of it. Which is fine, right? It's not a big deal. It's another process that will run on Saturdays and Sundays. Planet like. On non-eventful days, we'll run the compaction, maybe. I'm not sure. Anyway, there is no compaction on this. So there are file min key and file max key. Instead of that, we can use the Bloom filter. So to get something out of it. Right. So then we have load and store, block metadata manager. So there are a few functions that are going in for getting the data. So load and store is basically whenever it loads a block, it will cache it as well. So there is a caching thing happening over here. right? So once the cache is there, probably it is again LRU 100. It's basically 100 entry cache. Then another thing, probably what else happens is so that's how the get works. So coming to put, actually you have few more things to cover, right? So there are logs anyway. Logs are there. We cannot get rid of logs. At least whenever I was writing, I couldn't get rid of it most probably because there are always logs. Few logs are required, right? You're not locking indefinitely, but few locks are required. So should flush is a method whether you should flush or not. It's it will. So we use message pack encoding. If you dig deep into this code base, we have two types of encoding: Go binary and message pack. But right now we stick with message pack. There is no reason. I was using Go binary, then I was like message pack was there. So advantage is that message pack we can use other languages for decoding as well. Go binary is very dependent on Go. So anyway, so we use message pack and we have a persist current buffer. So which is a function to persist the current buffer and clear the buffer, create a new buffer. And entry the new things, right? Update metadata. A few calls are going whenever we want to, persist all these things. So this is, I think it is a bit heavy code over here. I think the is last block that there are a couple of logics over here that is required to, you know, um, write something into file systems, right? This is file metadata manager. This is write to buffer. So here you provide the block ID and the size, right? And file metadata block size. So it will what it will do, it will just basically encode. So there is some queue mechanism. But really, this is not really working. Or this is not really implemented. This queue, we can ignore it right now. This was when I was thinking to queue the buffers again in the cache and then later to push it, but it can increase the memory size. So that's why in the application layer, so I didn't do that. I'm just directly flushing it. So here, anyway, it knows it will pull out the entry from the buffer queue and claim the buffer. So this is how it writes the buffer right now. So there is write at this is the bytes, this is the block ID, the block size. So that happens. This is a file pool. This is an abstraction that I to try to create, but don't worry, we are not using this file pool cache. No, this is something that I was thinking. What if we store the pointers of os.file that we don't need to open or close or once it is and purge LRU will take care of because there is a eviction callback that will take care. I'm not sure. I was thinking maybe that can reduce the syscalls, but it doesn't make sense. It didn't make sense later, and it had issues. That is the prior main reason because after writing, it was not reading properly. It was not writing properly. So just ditch the cache. The implementations are still present for some reason because I don't want to remove it. So load is basically it will open and it will give you the file closer and error. So basically, file itself is a implementation of closer, and there is remove. Remove we are not using, so it's just basically this. We use this for our loading the file and then opening the file and reading, writing, all these purposes. Um, Probably the cool part of the code are in the block buffer manager. Maybe there are metadata manager. Metadata manager is also responsible for getting the metadata and couple of details what are there in these blocks, right? Um, yeah, that's the basic gist about most of this Go store. You can find all these in my repo in GitHub. I have pushed all these things into this Gostore APK. Um, so I think, yeah, more on this can be covered later. I think there are few, you know, better thought when implementing. So there might be a part two on how we can possibly implement it better, or what are my thoughts where we could have done something else, right? There are obviously many places, right? Yeah. Anyway, it was a nice attempt, I guess, right? We were able to successfully do this sort of storing and retrieving of the data. So anyway, yeah, that's it for this video, I guess. Yeah. Thanks for listening till the end. Um, yeah, thank you. Bye bye, guys.